All right, so topic 3.3, electromotive force and internal resistance. So what is electromotive force? So those of you who came a little bit earlier, who saw the beginning of the video, the definition of electromotive force was already given. I'll repeat it for those who weren't able, who came in just a little while ago. So the electromotive force, or EMS, is the energy transferred or work done by an electrical source to move 1 coulomb of charge in a complete circuit. Now, we will be talking about electromotive force and comparing it with voltage, because if you read the definition of electromotive force and then you go back and you read the definition of voltage or potential difference, it's almost the same. The words are almost the same, but there is a difference between those two. And not only are the words almost the same, the unit that you use to calculate electromotive force and the unit that you use to calculate potential difference is both the same. It's volts or joules per coulomb. Right. But there are some slight differences, which we'll look into later. So let me continue. So the electromotive force, EMF, is the energy transferred or work done by an electrical source to move 1 coulomb. So in a complete circuit. So once you have a circuit where it's going around and around. After you move 1 coulomb, right, which we learned is how many millions of electrons. After moving that many electrons in the circuit once, okay, how many joules of work have you done? So that's what electromotive force is. Where you can create the formula that looks something like this. So we have epsilon being the electromotive, not epsilon, but some character that looks like the letter E, right? So electromotive force equals energy transferred over the amount of charge flowing, so joules per coulomb. So like I said just now, SI unit of EMF is voltage or joules per coulomb. So once again, very similar to the formula for voltage. The formulas are similar, the units are similar, but here is where the difference is. And we will get into solving problems later. Right, so like I said, electromotive force and a potential difference have the same SI units, but there is a slight difference depending on the circumstances. And here it is. Right? I want you to go down to the lowest row and read the difference in the definition, right? The definition of EMF is this: work done by an electrical source to move 1 coulomb of charge in a complete circuit. All right, meaning to say, if you have a battery, how much work is being done to go from one end of the battery all the way throughout the circuit and then back to the other end of the battery. Right? So that's electromotive force. You have to go to the whole complete circuit to calculate the electromotive force. Now, the potential difference is work done to move 1 coulomb of charge, again, very similar, between 2 points. So the difference is when you're calculating potential difference of voltage, between 2 points, it does not necessarily have to be between the 2 points of the battery. It can be 2 points anywhere within the circuit. Right? Anywhere within the circuit. Now, if those 2 points happen to be the 2 points of the battery, then yes, you should get the same reading for potential difference and electromotive force. It would be same thing because you're using the same 2 points basically. But sometimes, if you were to calculate 2 different points in a certain area, let's say if it's a parallel circuit or series circuit, depending on the location, you might get a different reading compared to the total EMF or electromotive force that is rated on the battery. So that is the main difference. One is Work done by an electrical source to move one coulomb of charge in a complete circuit. So from one end of the electric source all the way around the circuit back to the other terminal of the electric source. But potential difference, it can be referring to potential difference anywhere in the circuit between any 2 points. Right? The other differences, so other differences is for electromotive force, you don't necessarily have to have a current flowing to measure electromotive force. For potential difference, you should have a current flowing in the circuit, right? So for electromotive force, you have the voltmeter reading in an open circuit and the voltmeter reading in a closed circuit for potential difference or voltage. But other than that, it's pretty much the same, right? So sometimes in some questions, there will be no difference between the potential difference and the electromotive force. In some questions, it will be slightly different, so you do have to read the questions carefully. Now we will be working on some example questions later. We'll go through the examples in the textbook. All right. Internal resistance. So we talk about EMF, right? EMF is, like I said, very similar to voltage. So we don't really need to spend too much time talking about that. You know what voltage is. And so EMF is quite easy to understand. Now, internal resistance. So based on activity 3.6, which we didn't do, right? But it's in your textbook and you can try to do it for yourself. But if you do certain types of experiments, certain types of testing, the value of potential difference across the bulb V is smaller than the EMF of the dry cell. So if you were to make a circuit and then you first measure the EMF of the dry cell of the battery, right? So usually it's written on the battery, right? 1.5 volt. So the EMF of the battery would be 1.5 volts. But when we put it in a circuit and then we measure the voltage across 2 points, let's say across a bulb, we find that the voltage, the potential difference across 2 points somewhere in the circuit is actually smaller. So meaning to say somewhere along the circuit, the voltage goes down. The voltage is reduced or there is a voltage drop. So the question is why? Right? Why is it that if a battery has 1.5 volts, then why is it by the time you check the voltage of or potential difference somewhere else in the circuit, why does it suddenly become lower? Why does it suddenly become 1.3? And the reason being is this thing, what we call internal resistance. So you all know what resistance is. You've learned Ohm's law already. You've learned that the higher the resistance, it causes a reduction in the current. Right? Now, before this, we've always done. How do I put this? We've always done our calculations assuming that all the components have zero resistance except the resistor. Kan, begitu kita buat kita punya soalan-soalan setakat ini. But the truth of the matter is this. Right? Internal resistance R of a dry cell is the resistance caused by the electrolyte in the dry cell. The truth of the matter is even a battery, inside that battery, it has its own resistance. Dalam sebuah battery, dia mempunyai rintangannya sendiri. Right? Because it's not a superconductor. Remember last lesson, we learned about what superconductors are and what a normal conductor is. Right? Even a battery does not actually have a resistance of zero. Okay? It might be very low, but it's not zero. So because of that, right, so because it's resistance, we are using the same unit as resistance, ohm. So what happens with this internal resistance? So one is we have loss of energy. So some of the energy is converted to heat in dry cells. as work has to be done to move one coulomb of charge against the resistance within the dry cell. So because there is resistance within the dry cell or within the battery, right? Because it's within the battery, it still has to fight or it still has to overcome. Dia masih kena mengatasi rintangannya sendiri. So not only dia kena melawan rintangan yang terdapat dalam perintang, tetapi dalam itu bateri sendiri pun ada rintangan sebenarnya. That's what we call internal resistance, because it's not from outside but it's from inside the electric source. Right? So because of this internal resistance, when we measure the potential difference, the voltage as we call it, across the dry cells, it tends to become less than the actual electromotive force, E, when current is flowing in a complete circuit. So let's think about it for a moment. Kalaulah kita mau cari the perfect battery, kita mau cuba mencipta, let's say kamu lain kali kamu kerja untuk, let's say next time you are working for a company like Tesla, specializes in electric cars. Okay? So bila kamu membina sesuatu seperti ini, these are things that you have to think about. Okay? Macam mana saya mau cipta bateri yang paling sikit dia punya internal resistance. Okay? Kita punya situasi yang paling ideal ialah, of course kita mau internal resistance to be zero. Right? So that we can avoid loss of energy. Tiada tenaga yang hilang menjadi haba. 100% tenaga itu akan menjadi tenaga kinetik untuk kendaraan bergerak. And no loss in voltage. So you get the maximum power from the battery. Right? Unfortunately, kita belum lagi ada bateri seperti itu. But I'm sure, of course, ini pembuat bateri, pembekal tenaga elektrik, of course, they are always doing research to try and find the perfect battery. So, yeah, it's caused by the electrolytes in the dry cell. Now, one thing to note is that, so this is the formula that we can use. So, the voltage drop, IR equals E, so E is the electromotive force minus the actual potential difference. Right, so again, electromotive force. So electromotive force would be what's written on the battery, for example, 1.5 volts. And then when you check the potential difference with a voltmeter, you might actually get something like 1.3. So then your voltage drop would be a total of, what would that be? Would be 0.2, for example. I'm just giving you a hypothetical situation here. Right? So this is the formula, or this is the full formula of determining the EMF and internal resistance of a dry cell. So voltage drop, like I said just now, equals IR, so I being the current, small letter r being the internal resistance, equals E, so EMF minus V, potential difference. If we were to rearrange the formula, you would get V equals negative IR plus the electromotive force. Yeah. So yeah, E equals electromotive force, V equals potential difference across the variable resistor. It doesn't necessarily have to be a variable resistor. It can be any type of resistor. Okay, I being the current, R being internal resistance of the dry cell, and R being external resistance. Okay, so there are two formulas here. The first one is this one, IR equals EV. So internal resistance, so we're only talking about the internal difference, internal resistance here. The other formula here is actually based on a substitution, right? So we could write it as, we could rewrite this formula. Let me actually show you how it's done. Okay, good. So what we could do, we could take the original formula. So current internal resistance equals E strange E, let's call it strange E minus V. So this is the formula for calculating the voltage drop. So we could rearrange it to focus on finding the voltage of potential difference. So potential difference should be V equals negative IR plus the electromotive force. We could also rearrange it so that the formula is focusing on just finding the electromotive force. So we could arrange it something like this. So electromotive force equals V plus IR. Okay, so so this is shape number one, or this is all the same formula actually, right? If you know this one, then you know this one. It's the same one. And you can also use this one. Now, here, what we can do, we could also substitute V. Remember what we learned before? V equals what? V equals IR. So that's something that we learned in form 2. So we could substitute V for IR. So you would get this formula. So V equals IR. So current with the external resistance plus IR. So current with the internal resistance, and we can factorize it to become IR plus small letter r. So these are the three. Actually, you really only need to know number 1 and number 3. So these two formulas, you try to take the time to understand and know what it looks like. So this is the first one that I was talking about, and this is the second one that I was talking about. Right. So all these formulas can be used in different examples and different circumstances lah. Okay. How many more pages? I have 9 more pages in the slide. Okay, and another way for you to do the calculations is by using a graph. So if you were to plot a graph, of V against I, V being the potential difference, I being the current, a straight line graph with a negative gradient is shown in figure 3.28. So you could use this equation. You could just use the equation and treat the equation as a linear equation. Y equals mx plus c. Just input all the values. You get V equals negative r, I plus epsilon. Right? So it's basically, you can also apply the formula to a graph. And the gradient will give you the negative r. So yeah. Important things. So what are the factors affecting internal resistance? All right, so the first one that we already discussed, or we already alluded to, is alkaline batteries that use potassium hydroxide electrolyte are twice as durable compared to zinc carbon batteries that use ammonia chloride. Different electrolyte causes the internal resistance of the two batteries to be different. So the first factor is what kind of electrolyte do you use inside the battery? Okay, so different types of batteries are using different types of electrolytes, and we know there are different types of batteries. We have alkaline batteries, we have zinc carbon batteries, and then we have lithium based batteries, NiCad batteries, all types of batteries that we use in all kinds of different electronic devices. And those things actually affect what is the internal resistance of the battery or of the dry cell. Okay, so depending on the type of chemicals and substances used, you might have a different amount of internal resistance. The second thing is, apart from the electrolyte used, the arrangement of the dry cells. also affect the effective internal resistance. Meaning to say that this is especially important when you have more than one dry cell. All right, when you have more than one dry cell, let's say you want to connect 10, 15 dry cells together, then how you connect the dry cells together, whether you connect it in series or whether you connect it in parallel, becomes very important. So here's another picture. It's a little bit small to see. If you have your textbooks, you can follow it along. But so we have basically 1, 2, 3, 4 and 1, 2, 3, 4 batteries. Each of the batteries has a similar amount of we have a similar amount of uh, resistance. Different amount of resistance. So 4 batteries, but according to how we calculate the resistance, you will have a different amount of resistance for the whole thing. So for example, let me just review it. So if we have 3 batteries and we connect them in, let's have 3 batteries. If we were to connect these 3 batteries in parallel like this, then we have R1, R2, R3. We've already learned that when we connect resistors in series, what your total effective resistance would be R1 plus R2 plus R3. Okay, if we assume that all of the overall each of the resistors have the same amount of resistance, then we would get a total of, let's just say 3R. So 3 times the amount of the resistance. Right? So if you have 4 batteries and you have 4 times the amount of the resistance, and more and more. But if we were to connect it in parallel, something like that, then instead of 3R, you would get what? 1 over R equals 1 over R plus 1 over R plus 1 over R. And so you get, what's this? 3R. And so resistance equals R over 3. Right? Now, even though we don't know the exact number, but just on simple logic alone, 3R is bigger than R over 3. Right? If we're assuming that R is the same thing, 3R is definitely going to be bigger than R over 3. So the thing about connecting dry cells in parallel is that your total internal resistance is lower, right? Even if you add more and more batteries, your resistance actually starts to get lower and lower. And this is in some electrical situations, they actually take that into consideration. That is why when you're doing wiring for a house, right, they are not going to wire everything in series. I mean, the first problem is if you wire everything in the house in series, then if you turn off one switch, the whole house turns off. But the second thing, and more importantly, is if everything in the house is wired in series, then every single component that has any kind of resistance gets added up very quickly. And you get a very high amount of total effective resistance, causing the entire system to get hotter and hotter and hotter until you start to burn down your house. That is why you are actually not encouraged to connect too many extension cords to each other. Kadang-kadang ada yang suka begitu kan, satu soket, okay, dia akan ambil extension and then tidak cukup tambah lagi extension di extension and then add another extension to the extension. Right? You're adding things in series and you actually might end up overloading and overheating the circuit. Now, of course, kita punya rumah ni, we have quite a high voltage. Here in Malaysia, we have about 240 volts in the socket. So, for most places, that is not an issue, but that is something to consider. So, higher resistance when you add up the dry cells in parallel. However, the total EMF, if we go back to the oh, my camera's working again. All right. If we were to go back to the graph, to this graph here, you can see that the total EMF is also affected. When we connect dry cells in series, the total EMF is U plus added. The way you calculate total EMF is also the same as the way you calculate the voltage. So if you have 4 dry cells in series, your total EMF would be 4 times. So each of the batteries, you add up each one and you get more total voltage or more total EMF. But when you have 4 cells in parallel, the funny thing is you don't actually increase the voltage. You're just you're just reducing the resistance. So you're reducing the resistance, so you'll still get more current, but you're not actually increasing the voltage. So yeah, so depending on what kind of application you might want to connect in parallel, you might want to connect in series. Right, so like I said, like what we just saw and what we just discussed, the arrangement of dry cells in series increases the effective EMF, while the arrangement of dry cells in parallel reduces the effective internal resistance. So you have to choose which one is more important. Do you want more EMF, more volt, or do you want less resistance? So depending on the situation, you might prefer one or the other. All right. So problem solving internal EMF and internal resistance of dry cells. So we'll just be doing the example in your textbook. So if you have your textbook page, what is this? What page is this? Page 121. There's one example given. So let's go ahead and read it. So figure 3.32 shows 2 circuits with dry cells arranged in series and in parallel. All right. It's given that the EMF of each dry cell is 1.5 volt and the internal resistance R is 0.5 ohms. Right? So you notice that they're actually using the same battery, the same 2 batteries, right? So the questions are: 1, compare the current flow in the 2 circuits. Okay. 2 is which arrangement of dry cells give a greater current, and explain why. So these are actually very practical questions. And then in B, the question is, if the figure is replaced with 3 dry cells in parallel, calculate the current, compare the current in the ratios of the 2 dry cells in parallel and 3 dry cells in parallel, and state the relationship between the number of dry cells arranged in parallel with the current in the circuit, and explain your answer. So let's do this step by step. Right. It's in your textbooks, but we're still going to go through it. Okay. So let's go on with the first question. So first question A. So the first question from A is compare the current in the 2 circuits. Right. So when we're calculating current, we first need to calculate the internal resistance. So first we need to calculate what is the total internal resistance in each of the circuits. So in circuit number 1, what is the internal resistance of the battery? And in circuit number 2, what is the effective resistance of the 2 batteries in parallel? Right? So that's the first thing that we're gonna find out. So, So let's throw. First, let's see. Okay, 2 dry cells in series. I'm just gonna write down series, but you can write down the whole thing. In the textbook, what it does, it writes down the whole thing in the textbook. So when you have two dry cells in series, then your total effective resistance, or RE, you have to add both of the equals R1 plus R2. So we have 0.5 plus 0.5. So you have a total of 1 ohm. Now let's try find for parallel. So of course we know that instead of R plus R, we use 1 over R equals 1 over R1 plus 1 over R2. So it will be 1 over R equals 1 over 0.5 plus 1 over 0.5. Or we could, we could rewrite it as basically we write it as 2 over 1, 2 over 1. So 2 over 1, you get 4 over 1. Flip it around. So R, effective resistance, would be a total of 1 over 4 or 0.25 ohms. So immediately, just from this first calculation, from this first comparison, you can tell that in series, even though we're using the exact same batteries, right? Just by based on how we calculate resistance, the internal resistance in series is higher. It's 1 ohm compared to the internal resistance in parallel. You get 0.24. So sorry, 0.25 ohms. So that's just from a pure mathematical perspective. You can tell that the parallel has a lower resistance. Then, once we know that, then we can try to find the current. So, I'm gonna erase most of this. So we know that the current for the series one, we know that the resistance is 1 ohm. Internal resistance is 1 ohm here. And over here, effective internal resistance is 0.25 ohms. Alright? So how do we calculate the current? We know that E equals I being current, R plus R. Alright, R plus R. So what is the value of, what's the external resistor? So if we go back to the picture, there is actually an external resistor of 10 ohms. So external resistance is 10 ohms. If there was no external resistor, kalau tiada perintang external kena pasang, then it would be 0. But since there is 1, so we use 10. So let's just write that down lah. Let's write that down. So R, external resistance, is 10 ohms. On the other side also, R equals 10 ohms. And so let's go back to the electromotive force. So electromotive force equals I R plus R. So I equals electromotive force over 10 plus 1. So 10 being the external resistor, 1 being the internal resistance, which we just calculated just now. And your electromotive force, E equals, there are two batteries, 1.5 volt each. And since they're in series, we add them together to get a total of 3. And so your final answer is 0.27 amps. So that is your current in the series connection. Now, how about parallel? So in a parallel resistor, parallel formation, you can use you basically are using the same formula. So I equals, now your total EMF that is only 1.5 this time. Even though we're using more batteries, it doesn't change because they're in parallel. So 1.5. Okay. Resistance, external resistance is still the same, 10 plus. Internal resistance is only 0.25. Right? And so what is your final current? Your final current is 0.1463 amps. So in our initial comparison, in our first comparison, in series, you'll end up with a higher amount of current. So kamu masih mendapat current yang lebih tinggi if you use a series compared to a parallel arrangement for batteries. Alright, so that means now that we have these two, we know that series is higher, you'll get a higher current than parallel. We can answer the second question, which is which arrangement of dry cells gives a greater current, and explain. So which one gives a greater current? The one that gives a greater current is the series. Arrangement. And why? Okay, because the dry cell connected in series provides a higher current because of a higher effective EMF. So you get a higher total amount of EMF or electromotive force. Therefore, you get a higher total current. Okay, I hope that is clear so far. If there's anything that you're not so clear with, go anytime. Feel free to ask a question or type something in the chat. So that is the first part of bahagian A. So bahagian A, we're just basically comparing the two pictures in the graph or in the figure. Now B is now asking you to compare another circuit, a different circuit that's not in the picture. So let's read what it says. If the circuit is replaced with 3 dry cells in parallel. So the question is now, what if we add one more battery in parallel? Calculate the current. Okay, compare the current in the arrangement of 2 dry cells and 3 dry cells, and state the relationship between the number of dry cells arranged in parallel and the current in the circuit, and explain your answer. Right, so A, let's start with question A. So the question is, if we have 3 dry cells, what it would be the current? Okay, so let's check our information. So we know that each dry cell is 1.5. We know that the inner resistance of each dry cell is 0.5. So first of all, we need to find the total effective resistance. So effective resistance, what is the total effective resistance? So since we have 3 batteries, we'll have to add 3 times. So 1 over 0.5 plus 1 over 0.5 plus 1 over 0.5. So basically 2, 2, 2, 1, 1, 1. So you get 6 over 1. So total effective resistance is 1 over 6 ohms. 1 over 6 ohms, or you could also rewrite it as, your textbook writes it as 0.167 ohms. Right? So you can use either one of these. I like to use the fractions for calculating, but either one is actually fine. Okay, so that is the first thing. So now that we have calculated the effective resistance, now we can go back to calculating current. So current, we use the same formula as what we used just now, which is I equals E R, so external resistance plus internal resistance. Okay. Now, even though we're using more batteries, because it's in parallel, the EMF does not increase. You do not add the EMF together. You just maintain the same amount of EMF. So you still only have 1.5. Okay. External resistance is 10. Internal resistance now is 0.167. And so you get a final answer of 0.1475 amps. Right? So here we have 0.1475 amps. So now, back to the second question is, now that we've calculated the current, okay, there's a question here. Let's see. So in a series arrangement, the internal resistance is higher. So shouldn't the current be lower? Okay, so good question. Kenapa pula? So yes, you are right in that the internal resistance is higher. Memang dia punya resistance is higher. But with the increase in resistance, you also get a higher voltage. Kamu punya voltage secara keseluruhan juga bertambah. If you go back to even Form 2 science, right? If you remember, voltage in a series arrangement, voltan dia akan bertambah. So for example, kamu ada 3 battery, let's say each battery is 1.5. Dalam susunan series or berseri, if you have 3 batteries in a row, dia akan bertambah. So 1.5 plus 1.5 plus 1.5. So you get a higher total voltage of 4.5. Now, since V equals IR, semakin tinggi dia punya voltan, semakin tinggi juga dia punya current. So, even with the higher resistance, the higher voltage makes up for it. So the current will still, so you still end up with a total higher current, even though the resistance also goes up. Now, it's possible that in some situations you might get a situation where the internal resistance is so high that adding another battery would make the current lower. But in this particular situation, and I believe in most situations, increasing the voltage should be enough to increase the current. So that's the answer to your question. Yes, the resistance gets higher, but the voltage, because remember, the higher the voltage is basically more voltage means more power to fight resistance, basically. So when you have high voltage, a higher voltage is also able to handle a higher amount of resistance. That's a good question. All right, so back to our question just now. Okay, so compare the current in the arrangement of 2 dry cells in parallel and 3 dry cells in parallel. So we already calculated earlier the current of 2 dry cells and current of 3 dry cells. So 2 cells. So it's just a very simple comparison. So for 2 cells, we get a current of 0.1463, and with 3 cells, you get a current of, let's call this I1, let's call this I2. You get a current of 0.1475. Okay, the difference between these two. Okay, so with 3 cells, you get more current, basically. So if we were to if we were to make a comparison, we could write it simply as this. Or we could write it down as a sentence. In the example, it just writes it. The current of 3 dry cells arranged in parallel is higher. Right? And so now the question is, back to the... So the third question is state the relationship between the number of dry cells arranged in parallel with the circuit and explain your answer. So based on the calculations that we just did. So berdasarkan pengiraan yang kita sudah lakukan tadi. Okay. Increasing the number of dry cells arranged in parallel, bila kita semakin banyak sel kering disusun dalam cara parallel, with the we also increase the amount of current, right? And why does it increase the amount of current? Because by adding more batteries, you actually reduce the resistance. So the explanation would be, I'll just read what's written in your textbook here. Increasing the number of dry cells that are arranged in parallel, so semakin banyak bateri kamu tambah, okay, will also increase the current in the internal circuit. Dia juga akan menambahkan current because the effective internal resistance decreases. So, and this can also be related to what Henry was asking just now. So basically, what we see here in electricity is ada dua cara, or there are two different ways for us to increase the current. Okay, either keep the same amount of voltage but reduce the resistance. That means add more batteries in parallel. Or another way you can increase the current will be add more batteries in series. So you have a higher total voltage. So sebab voltan kamu lebih tinggi, dia juga akan menyebabkan kamu punya aliran or your current to be higher, but at the same time also cause your internal resistance to be higher, which means in practical terms it will generate more heat. It will have more total power, but you'll also waste more energy. Whereas if you connect a lot of batteries in series, you would end up basically with less power, but it's more effective. You're wasting less energy because there is less resistance. So those are the practical differences between the two types of arrangements for dry cells, whether you arrange it in series or arrange it in parallel. Actually, there's not much difference when we're calculating the resistance of batteries. Even if it's internal resistance, there's not much difference with calculating just normal resistance of a resistor ataupun perintang dalam 1 liter. It's basically the same. It's basically the same formulas that you're using, just that you're calculating internal resistance versus external resistance. Okay, what else do I have to talk about? So yeah, this is what we were talking about. It's not very clear in your slide. Let me try to zoom in and hopefully that'll help. So this is just a quick addition of electric power. Since we're talking about batteries, the topic also talks about electric power in vehicles. Electric vehicles have become very popular in the last few years. When I was in school, when I was a student, an electric vehicle is considered like super high tech. Like you only see like electric vehicles as prototypes or as experiments, but not something that you would sell to the public. This was when I was still a student. Nowadays, especially with companies like Tesla, so I guess Tesla would be the most famous electric car brand, but other companies also have electric cars now, electric vehicles. So basically, we have two types of electric vehicles. So we have electric vehicles that use 100% battery power using rechargeable batteries to supply energy to electric motors. So usually they're using lithium or NiCad batteries. So you need a high amount of voltage for electric cars. So like 300 to 800 volts. So a lot of the Tesla cars are using pure electricity, and there's a picture here. So basically it's just a big battery and an electric motor, and you have to charge your car every now and then. So here in Malaysia, since electric vehicles are not as popular yet here in Malaysia, we don't have many charging stations. Tidak banyak tempat untuk charge kereta. So I think I know that there are some people in Malaysia that have Teslas, but probably what they do is that they just charge it at home, I guess. Maybe they charge it the same way they charge dorang punya handphone. Ada dorang punya charger. But in America, oh yes. Okay, so good question. So I'll repeat the question. So so basically dia punya sama kah ini electric car? Sama saja macam itu kereta RC yang remote control, iaitu when we were kids, and I don't know if you guys did that, but when I was a kid, what we do, we take those cars. Sometimes what we do, we will take out the motor from the car. We take that out, or if we found a car that someone threw away, we'd take out the motor, and then we would use the motor to create all kinds of things. Like you could connect those motors to like gears or fans or something, and then you could connect it with a battery, and you'll still move. And so the question is it the same concept? Basically, yes, it's the same concept, except with a bigger battery, with a bigger electric motor, and probably a slightly different design for the electric motor. I'm not sure what kind of design they're using, but it could be that they're using slightly different design. But I imagine it's pretty similar. Yeah, and of course they're using things like gears, and they're using things like gears and gear ratios and other things too. Also, to also control things like the total force output and horsepower. But yes, the concept is more or less the same. For a pure electric motor, if we're talking about a pure electric car, all right, the other type of car that we're talking about would be the hybrid car, right? So the hybrid car, instead of 100% of the power being supplied by batteries, only about 25 of or up to 40% is supplied by rechargeable batteries. Now, hybrid cars have been around longer than electric vehicles. So hybrid car has been around for longer, and so basically what it does is it's a combination thing. It's a combination of a petrol tank using petrol and a battery, and it's still, if you buy one of these hybrid cars, you still end up paying a lot less for gas. So like a normal car might be able to go like between 20 to 40 kilometers per liter of gas. But a hybrid car, you might be able to go like over 100 kilometers per liter of gas, because the other kilometers are being provided by electricity. And these are just two types of designs, okay? There are other designs such as using electricity to create hydrogen gas from water, and then using the hydrogen gas to power the car, right? So you still burn something, right? You're still burning something to move an engine. So it's not like a pure electric motor car like this one, but it's not using like gas. So there are other different types of designs for electric cars. It's not just one design. But of course, now what they're trying to come up with is, of course, this pure pure electric cars, which they are using now. Uh, I remember this is a little bit off topic, but bear with me. So I remember one of the earliest electric cars is the Toyota Prius. You could try and Google that. Toyota Prius, Prius. Actually, let me look for it. Toyota Prius. Toyota. So, uh, so this is one of the first like well-known electric electric cars. Let me just show you the picture. So this is the Toyota Prius, the first generation. So when these Toyota Priuses started coming out, some people like to make fun of it, because the old Toyota Prius was, first of all, it's quite small. It's not like a really big car. And if you look at the shape of the original Toyota Prius, it's not the most stylish looking car, right? I mean, it's okay, but it's like not the most stylish in terms of style lah. And even in my opinion, in terms of style, it's not like the most stylish car. And the thing that people make fun of it is not only is that it wasn't the most stylish, it wasn't very like fast. Like it's not very fast. Kalau orang dusun bilang tidak begitu lajak. Yeah, if you buy a petrol car, you press on the gas, you can accelerate a lot faster. And this Toyota Prius, it just wasn't that powerful when it first came out, and it was very silent. So sudahlah tidak kuat, it was very silent. So people would make a lot of fun of it. But nowadays, of course, we have the Tesla. All right, so Tesla, which is much more stylish, much more powerful, and much more high tech. Right, much more high tech. And what did Henry find? Prius drag car. Right. So okay, that's interesting. Let me show you guys what Henry found. So here's something where they modified the Prius into to become a drag car. So those of you know what drag cars are. Drag car racing is basically trying to make the fastest car, trying to make a car that can move fast as possible in a straight line. And drag car racing is very short distances. So like, I don't know, maybe 200 meters for a car. So in these kinds of short distances, it's very important to be able to accelerate as fast as possible. So of course, any car, people will modify it. For example, this picture on the right, someone decided to put like monster truck tires on a Prius. So of course it's possible. Nothing is impossible. When it comes to modifying cars, people who have a hobby of modifying cars, they'll do crazy things. People used to make DIY hydrogen cars. You can find it on YouTube where people make like DIY hydrogen cars, which is to me just crazy. Like, how do you even make your own DIY hydrogen car? Like, how many explosions do you have to test before you get the correct type of car? But yes, there are such things as Prius drag cars. But back to where I was. Even after modifying those Prius cars, they're still, of course, not as like stylish and high tech as the latest generation of Tesla cars and other electric cars. And I was reading the article the other day. They are even planning to make like sort of Bluetooth put like Bluetooth microphones and put Bluetooth connections on Tesla, so that when you pass by another Tesla driver, they'll automatically automatically connect and you can talk to each other. I'm not so sure if that's a very good idea, but those are just some of the things that they are planning to, So cars are becoming very high tech these days. Um, but probably the interesting thing is if the electric cars are powerful enough for places like here in Sabah, in places like in the States where they have a lot of very flat roads. When I say flat roads, I mean like 15 kilometers of straight road. There are places there where you can drive a car and for 15 kilometers the road is just flat and straight. You cannot get those kinds of roads here in Sabah because there are just too many hills. But in America, there are roads like that. So when you have a flat road like that, power is not as important. It'll take you longer to reach the correct speed. But once you reach the correct speed, you can just maintain the speed for like 15 kilometers. There's less of a problem there. But like here in Asian countries where there are lots of hills, power is more important. Right. So yeah, like I said, a little bit off topic, but interesting discussions for future developments. And to come back to our initial topic, uh, if you look at your textbook, there's actually a discussion about how they would connect the batteries for these kind of vehicles. Whether or not the vehicles, whether you'd use a series connection or uh, whether you'd use a series connection for the batteries or whether you'd use a parallel connection or if you would use maybe like some sort of combination of the two. So they have to think like, do I need more voltage or do I need less internal resistance? Because they want the idea of a hybrid car, right, is to be most efficient. So use very little, or rather get as many kilometers as possible from as little electricity or as little power as possible. That's kind of the idea of the electric vehicle. And so they have to think, do I need more voltage but increase the internal resistance of the battery, or do I try to put more batteries in parallel so I have less internal resistance but I have a lower total voltage? These are things that car manufacturers, or I should say electric car manufacturers, have to consider. And of course, the ideal situation is to find a battery that has high voltage but zero internal resistance, which of course, like I said, we don't have yet. So yes, so electric vehicles and hybrid cars can be charged using domestic electricity supply. So you could connect it to a charger, and at electric vehicle charging stations, or at a solar cell charging power station. So here in Malaysia, we don't have that many yet. But in the States, they have a lot of... they don't have gas. They have gas stations in the States, but they also have electric stations now in the States for you to charge vehicles. So yeah, that's great. Yeah, we know what solar cells are. So here's something. So the arrangement of solar panels at the solar cell are arranged in series. So for when it comes to, at least when it comes to solar cells, they choose to prioritize getting a higher voltage. Probably because each of the solar cells by itself does not have a very high voltage, right? So since each of the cells does not have a very high voltage, they need to get a higher voltage as much as possible. So yeah, the use of EV electric vehicles is a good alternative in maintaining an environmental sustainability. So yeah, the argument is electric cars are more environmentally friendly because you're using less gas. Now, whether or not, and of course there's an argument to be made, and we're not going to go too deep into this, but of course there's an argument to be made, yeah, that says that even though the electric car is not burning as much fossil fuel, tapi the fossil fuel that you need to burn to charge the car is still producing the same amount of carbon dioxide. So there's a bit of an argument there of course. And there'll always be, when it comes to electricity, when it comes to sustainable, that's one of it's a global nowadays. It's a global, I guess you could call it a global debate. Like, what is the most sustainable source of energy? And of course, it gets worse when money comes into play. Like, of course, big companies that uh, make a lot of profit from things like gas and oil. Of course, they don't want electric. They don't want like electric clean energy to become too developed, because then they'll have less less people will buy gas from them, and they will not be as rich anymore, right? So world economics is a complicated thing, right? And it even affects things like environmental sustainability, which is why it's a big debate all around the world. All right. So formative practice 3.3. I'm not going to ask you to do this homework, because we can just review this right now. So what is meant by electromotive force? We just discussed it like earlier. So electric motive force, to just as a reminder, is the amount of work done by an electric source to move one coulomb of energy throughout a circuit, right? Throughout the whole circuit. So from one point of the battery to the other. Okay, the difference between the potential difference can be just between any point. But for electromotive force, it has to be throughout the whole circuit. So yeah, we just stated the difference between EMF and potential difference. What is the effect of internal resistance on current in a complete circuit? So internal resistance causes voltage drop, and reducing the voltage also causes the current to be reduced. And the last one is, if you are supplied with two dry cells, what type of arrangement can reduce the effective internal resistance of the dry cells? So if you want to reduce effective internal resistance, you would arrange it in parallel. If you wanted to arrange it in, I'm sorry, if you wanted to arrange it in, if you wanted a higher total voltage, then you would arrange it in series. All right. Okay, so that's our whole class for today. Yeah, and this time it's almost 9 o'clock already. So